So in this video, we are going to review or learn how to represent acid-base reactions graphically using free energy diagrams and talk about how to recognize how likely it is that a reaction be reversible or not. So here is a slide summarizing kind of the anatomy of a energy diagram for an acid-base reaction. So let's go through all this information step by step. Here is an example reaction of HCl with water. We know the mechanism for this reaction. The lone pair on water reacts with the proton, and the lone pair goes back to the chlorine, and we get our products. Okay, so these are reactants. On the right, we have products. We will draw an energy diagram that looks like this. So our diagram has two axes. The first one down here on the x-axis, down at the bottom, we call that our reaction progress. That is not time, it's reaction progress. It's how are we going along in transforming our reactants into products. And I'll talk more about that in a minute. So that's our reaction progress. And then we have on our y-axis in blue and some measure of energy. We can talk about that in terms of delta H, which is enthalpy, or delta G, which is Gibbs free energy. I know that those words don't mean anything to us right now. We just have to label it something. We're going to label it delta H, okay? We'll talk more about why that is in class. Now we have our reactants. Our reactants are shown here, A and B. I'll label our A and B like this, acid and base species. We place those on the graph at a starting point here. Our products, let's do that in green. Products are what we'll call C and D over here, and those go on the graph here, okay? And so what we see is as we are transforming A and B, acid and base, into products C and D, it requires an input of energy to do that. We see that because we're creating a hump on our energy graph. The energy is going up and then it comes back down, okay? Right here at the tippy top of our mountain or our hill, we call that the energy of the transition state. At that transition state, that is the moment that the lone pair from our oxygen on our water is grabbing onto that hydrogen, and the bond between the hydrogen and the chlorine is breaking. So it's the moment that the sticky lone pair is gluing to the hydrogen and the second bond is breaking. When that happens, we are at the transition state. It's the moment that we're transitioning between being acids and bases and conjugate acids and conjugate bases. There's an energy associated to that. We call that the activation energy. I'll do that in orange. The energy change from where our starting materials were and how much energy needed to be put in to do that transition, we call this the transition state. You might also see it marked like this, a TS with this little dagger sign to note the transition state. Okay, so here's all our pieces. Let's look at an example. So here is an acid-base reaction that we are very familiar with. I expect at this point you recognize HBr is a strong acid and O- would be a strong base. They are going to react to form the products over here. I'm going to call those products C and D. Let's put this on an energy diagram. Let's start by drawing our axes, X and Y. On the x-axis, we have reaction progress. Not time, reaction progress. On the y-axis, we have energy. when we're talking about acids and bases, we can use delta H, which is the enthalpy of the bond. That is a measured amount of energy in the bond that we are talking about. That's what enthalpy is. So now let's place these on our graph and start to work towards representing this graphically. Let's start by putting our A and B acid and base here. There's a required amount of energy to deprotonate that hydrogen and make it bond to the O-. Call that the transition state. And then we get down here to our products C and D. Okay, so our parts here, we have our transition state, and I'll use orange to show the activation energy. That is the energy required for reactants A and B to get to that transition state over that energy hump to become the products. And we always mark it from where the starting materials or our reactants are up to the transition state. That is a noted amount of energy that is required to do this reaction, okay? So now how do we know whether to draw it like that, or maybe we would draw it like this? How do we know that A and B are lower or higher in energy than C and D? Well, think about your pKa's. So the pKa of HBr is -8. The pKa of our acid on the other side is the OH of an alcohol is about 16 or 17. So the higher the pKa, the weaker the acid. And so we know that the equilibrium tends towards the weaker side. So we would draw, I'm going to erase this equilibrium arrow, draw an equilibrium arrow that looks like this. This is going to be product favored. To the tend towards the product side is going to be the weaker side. So the products are going to be the more stable. So we'd expect them to be lower in energy. So the first graph I drew shows our products lower in energy than our reactants. So that's why we would not represent this graph like the one I drew on the far right there, because that has the products being higher in energy than our reactants. We know to predict, based on our predictions of our conjugate bases and our strength of our acids, that our products are more stable. So we would represent it this way. Now I've taken that same reaction, the reaction we just did with HBr and O-, and I've changed the sides. This is going to be our reactant now, and this is going to be our product. Okay, we're doing the reaction the other way, right? And so let's look. We know that the pKa of an alcohol is about 16. The pKa of HBr is about -8. So, but based on how this is set up, this is going to be tend to the weaker side. This is going to be a reactant favored. So if the reaction was given to you like this, we would need to draw a graph that represents this change. Something being reactant favored would have lower energy reactants. So we'll use our same kind of green to represent our reactants, our acid and our base. And we have some kind of starting material or some kind of activation energy. And we know that our products in blue are higher in energy. They are less stable than our reactants. So we need to put our reactants, or our products, C and D, higher in energy. Well, now how do we make sense of our transition state? Well, our transition state is still the energy associated with this hump up here, but our activation energy now, going from our reactants up to that transition state, that's our activation energy now. Okay, that is our activation energy. And it is large. It is larger than it was when we went the other direction. That makes sense because if we're trying to move our reaction in a way that is less stable, there would be a larger activation energy required, a larger input of energy required. Okay? And so when we look at these reactions side by side, this reaction where the products sit higher in energy than our reactants, I forgot to label my axes. You must label your axes. When we have our products sitting higher in energy than our reactants, like we do here, we would call this is delta H is positive, because the difference here between here and here is positive. We call this endothermic. On the last slide, when we saw our reactants up here and our products down here, the difference in energy between our reactants and products here is actually negative. So we have a negative delta H. We call that exothermic. Exothermic.